I never fully got why black holes slow down time. It always felt like a piece of science fiction, a concept so bizarre it couldn't possibly be real. But it is, and the reason why is one of the most profound ideas in all of physics. Tonight, we're going to gently bend your intuition, stretching it until you can feel time itself warp, tick by agonizing tick, at the edge of a cosmic abyss. This isn't just about memorizing facts, it's about building a new kind of understanding. So, stay with me. First, a quick but crucial setup. We need to throw out our old idea of gravity. Isaac Newton saw it as a mysterious force, an invisible rope pulling things together. But Albert Einstein gave us a revolutionary new picture. He said gravity isn't a force pulling on you, it's the shape of the universe itself. Massive objects like planets and stars literally warp the fabric of space-time around them, creating what we call a gravity well. Imagine a bowling ball on a trampoline. That's the sun. A marble rolling nearby will curve towards it, not because it's being pulled, but because it's following the curve in the fabric. Now here's the leap. This curvature doesn't just affect space, it affects time. Einstein realized that space and time are woven together into a single entity, space-time. So, when you curve space, you also curve time. The rule is simple but has wild consequences. The deeper you are in a gravity well, the stronger the gravity, the slower your clock ticks relative to someone in a shallower part of the well. It's not a suggestion, it's a fundamental law of the cosmos. Near a black hole, this concept is pushed to its absolute limit. A black hole isn't just a deep gravity well, it's a bottomless pit in space-time. The curvature is so extreme that it creates an event horizon, the point of no return. As you drop closer to this boundary, your clock begins to slow down dramatically compared to mine, watching safely from a distance. For every hour that passes for me, only minutes might pass for you. The closer you get, the more extreme this difference becomes. But why? How does this actually work? The key is light. Imagine you have a flashlight, and you're sending me one pulse of light every second. From your perspective, that's exactly what's happening. But as those light pulses climb out of the black hole's immense gravity, well, to reach me, they have to fight against that curvature. This cosmic climb costs them energy. For light, losing energy means its wavelength gets stretched out, shifting it towards the red end of the spectrum. We call this gravitational redshift. Because those light waves are stretched, they arrive at my telescope less frequently. Instead of receiving a pulse every second, I might receive one every 2 seconds, or 10, or 1,000. From my point of view, it looks like your flashlight, and your clock, and your heartbeat are all running in slow motion. Your clock isn't broken, it's just that the very signals it's sending are being distorted by the warped space-time between us. My clock sees yours as slowed. Now let's add another layer. You might have heard of time dilation from speed, a concept from Einstein's special relativity. The faster you move through space, the slower you move through time. Near a black hole, you get a devastating 1-2 punch. You get time dilation from both gravity and velocity. Imagine you're not just falling in, but you're in a spacecraft trying to orbit the black hole as close as you dare. You'd have to travel at a significant fraction of the speed of light just to stay in orbit. So, your time is already slowed by your incredible speed. On top of that, you're deep inside the gravity well. The two effects compound, stretching your seconds into what would be minutes or hours for a distant observer. This isn't just a theoretical curiosity, it's a plot point in some of our most beloved science fiction. Think of the movie. The crew lands on a planet orbiting a supermassive black hole. They spend just a few hours on the surface, but when they return to their ship, decades have passed for the crewmate who stayed in a higher orbit. That wasn't just movie magic, it was a dramatization of real physics. The planet was so deep in the black hole's gravity well, and moving so fast, that time for them slowed to a crawl compared to the universe outside. And it gets even weirder. Most black holes aren't just sitting there, they're spinning, some of them incredibly fast. A spinning black hole, known as a Kerr black hole, does something truly mind-bending. It drags the fabric of space-time around with it. This effect is called frame dragging. Imagine a spinning ball dipped in honey. The honey right next to the ball gets pulled along for the ride. Near a Kerr black hole, space itself is being pulled around in a giant, inescapable vortex. This cosmic whirlpool doesn't just affect your path, it further warps the flow of time. Let's run a thought experiment to make this concrete. Imagine two twins. One, let's call her Stella, stays in a spaceship orbiting safely far away from a black hole. Her twin brother, Alex, takes a smaller ship and swoops down for a close, fast orbit right near the event horizon. He stays there for just 1 hour according to his own watch, then fires his engines and escapes back to Stella's ship. When they reunite, Alex will be younger than his sister, not by a tiny fraction of a second, but potentially by minutes, hours, or even years, depending on how close he got and how fast he was going. He experienced 1 hour, while she lived through much, much more. Now, let's bust a few common myths. First, you can't just hover right at the event horizon to watch time pass. To stay in one place against that infinite gravitational pull would require an infinite amount of thrust from your engines, which is impossible. From my distant perspective, as you tried to approach and hover, your spacecraft would appear to slow down, your light would get redder and dimmer, and you would seem to freeze in time, eventually fading into blackness. You'd be a frozen, red-shifted ghost on the edge of forever. But, and this is the most important part, for you, the astronaut, time would feel completely normal. This is the core of relativity. Locally, your time never changes. Your heart beats at its normal pace. Your watch ticks 1 second at a time. You wouldn't time slowing down. It's only when you compare your clock to a clock in a different region of space-time, like Stella's, far away, that the mismatch appears. Time doesn't break at a black hole. Different perspectives on time simply diverge, dramatically. This leads to our second myth, that if you fall into a black hole, you get to watch the entire future of the universe unfold before your eyes. It's a cool idea, but it's not what happens. As you fall past the event horizon, you don't get a cosmic fast forward. Instead, the light from the distant universe would become increasingly blue, shifted from your perspective due to your acceleration, but you'd cross the horizon in a finite amount of your own time. The journey to the central singularity would be swift and final. No front row seat to the end of time. If this all sounds like abstract theory, I have a surprise for you. You use it every single day. Want a down-to-earth taste of time dilation? Just use your phone's GPS. The GPS satellites orbit about 20,000 kilometers above us. Because they are higher up in Earth's gravity well, their internal clocks actually tick slightly faster than clocks on the ground, by about 45 microseconds per day. This is a real measurable effect of general relativity. At the same time, those satellites are moving at 14,000 kilometers per hour. Because of their speed, special relativity says their clocks should tick slower than ours by about 7 microseconds per day. Engineers have to account for both of these effects. They deliberately build the satellite clocks to run slightly slower in the factory, so that once they're in orbit, the combined effects of gravity and speed make them tick at the right rate to sync with us on the ground. Without these relativistic corrections, your GPS would be off by about 10 kilometers every single day. We also see this happening in deep space. At the heart of our own Milky Way galaxy lies a supermassive black hole called Sagittarius A. For decades, astronomers have been tracking the orbits of stars whipping around it. One star, called S2, gets incredibly close. As it swings by the black hole, we can actually measure the gravitational redshift in its light. Its light gets stretched just as Einstein's theory predicts. We are directly observing time being warped by a black hole. So let's bring it all together with a final metaphor. Picture a metronome, setting a steady rhythm for the universe. Far from any gravity, it goes tick, tick, tick. Now, move that metronome closer to a black hole. As it sinks deeper into the curved spacetime, an outside observer would see its rhythm change. Tai, K, Tai, K. The closer it gets to the horizon, the longer the pause between ticks, stretching towards infinity. It's the same device, the same physical mechanism, but it's operating in a place where the very beat of time itself has been slowed. From far away, you seem to freeze at the edge, your light smeared out and redshifted into eternal darkness. A static image pasted onto the horizon. But from your perspective, your own time carries you forward, smoothly and unstoppably, across that invisible line. In that moment, your future is sealed, but your present feels completely, utterly normal. Two perspectives, one reality, separated by a chasm of curved spacetime. So now, hopefully it clicks. Black holes slow down time not through some strange magic, but because they warp the fabric of spacetime so extremely that the rhythm of everything, clocks, light, life itself, is forced to slow down with it. It's a consequence of the universe's fundamental geometry. Next up, we'll explore what happens to the matter that gets too close, forming brilliant accretion disks and powerful jets, and how we use them to see the invisible. Time bends.